everyone. Thank you for joining us. Today's webinar will provide an overview of the new security features included in OpenDDS version 3.13, which was released just this morning. Your presenter is Adam Mitz, Principal Software Engineer at OCI and OpenDDS Project Lead.
All right, thank you, Nikki, and thanks everyone for joining us. So this morning we're going to talk about revolutionizing data distribution with an open and secure DDS. So we need to start with a little bit of background information. For some of you, this may be review, so please bear with us on it. OpenDDS is an open source and widely adopted standards-based real-time publish-subscribe solution for distributed systems. The project homepage is listed there, opendds.org, and we're hosted on GitHub under Object Computing OpenDDS. Second. Developers use OpenDDS as a framework to enable their C++ and Java applications to distribute data over the network using a publish-subscribe architecture. Unlike low-level transport protocols, the OpenDDS middleware is aware of the schema and semantics of the data. OpenDDS helps shield application developers from the inherent complexities of distributed computing. To take a look at what this really means for application architecture, we're going to count on some resources provided by the Industrial Internet Consortium. The Industrial Internet Consortium, IIC for short, has published a connectivity framework that defines a stack model consisting of multiple layers. The DDS API sits at the framework layer, providing syntactic interoperability among heterogeneous systems. DDS products also include an interoperable standards-based transport layer that provides technical interoperability. Let's take a look at that graphically here. So not only is there a transport layer shown in green, but there's also the framework layer shown above it. Many alternatives to DDS provide only that transport layer, requiring each application to provide its own solutions to those concerns in the framework layer. Let's take a look at these in a little more detail. In this low level, the connectivity transport layer, we have the protocol itself and the ways that those protocol messages reach peers across the network. So endpoint addressing and prioritization. Security is important here, of course, because that's happening down at the network layer, and we'll get into details of that shortly. So all of this is happening within that transport layer. Now, if we go up a layer and look at the details of the framework, here's where we have things like quality of service, governance, the API, the publish-subscribe model, the way discovery works, having a type system, and state management. And of course, security shows up here too, because the security aspects need to be configured and understood at the framework level and not just down inside the transport. So DDS can provide applications with this sort of framework, and now DDS Security adds security to it as well. So to continue with the DDS overview, the OMG DDS is a standard provided by the Object Management Group, and OpenDDS is the implementation of that standard. The DDS specification describes the API and its semantics, but not how to exchange data over the network. That interoperability over the network is made possible through a separate specification called RTPS. It defines a standardized discovery mechanism and a wire protocol for DDS. We'll see how security fits into that when we get there. So first, some brief notes on OpenDDS as a software project. Development started back in 2005 by us here at OCI. Version 1.0 was released in July 2007. That's where it got the name OpenDDS. We have more than 15,000 commits in the Git repository, both internal and community contributions. Our GitHub repository is the site of active development. We're not just publishing snapshots. We have continuous integration builds to automate testing on many platforms and compilers. There's community support. Our GitHub hosted site, opendds.org, is available for the community to both use as a resource, but also you can propose changes to it through GitHub. And we use issues and pull requests on GitHub and mailing lists hosted by SourceForge. We also offer commercial support, custom development, and training here at OCI. So before we get into details of security, a quick review of DDS terms and concepts. So DDS provides this idea of a global data space, the cloud at the center here. And different DDS applications can connect to that through these objects: publishers, subscribers, data writers, and data readers. In this presentation, we won't be too concerned with the APIs and the ways that the writers and readers actually work in your source code, but we will look at how DDS security impacts this. Keep in mind that in the DDS system, each individual data writer or data reader belongs to a topic. Topics have a certain data type, and this all exists within a domain. Since these DDS applications share data over the network, without DDS security, this is just happening in the clear. And this has worked for many years, but it makes these traditional DDS applications require a closed network or networks that provide their security separate from the application space. This could be done using VPNs, tunneling, that sort of thing. Now with the DDS security specification, DDS can use industry standard cryptographic algorithms and techniques to protect applications from these specific threats: unauthorized publication subscription, tampering replay, and unauthorized access to data. This is very similar to what we're more familiar with, HTTPS. However, the DDS with RTPS security is running over UDP IP and supports multicast, including with encryption. So DDS security builds on DDS RTPS, just as HTTPS builds on HTTP. So from a software architecture point of view, the DDS security builds on top of what's already provided, and it does this using plugin APIs. The security spec defines these plugin APIs for authentication, access control, and cryptographic operations. The specification also defines how the built-in implementations of these plugins should work. So as you'll see on this side, when you download and build OpenDDS with security, you'll have these various components. At the bottom of the stack are all the libraries that we depend on, then the OpenDDS core, followed by the RTPS support that's been in OpenDDS for years, and now the new security support sitting on top of that. In this presentation, we will assume that the built-in plugins are the ones being used. That's what's most commonly done with DDS security, but developers could also write their own plugins. Let's look at what the security specification provides in a little bit more detail. There are really these three key areas: authentication of participating applications. So an application's identity is determined by certificates that are signed by a common certificate authority. Then access control. This can be done at the topic level. Configuration files that are signed by the CA determine which applications have access to which topics. And the third major area is the data protection, which happens through encryption and/or message authentication. Again, this can be configured per topic, and it can determine whether to encrypt or to only sign messages as they go on the network. The scope of data protection is also configurable. It can be payload only or include headers. And we'll see details of that when we get to that point. Let's look at some more technical aspects of what's happening with the built-in plugins. The built-in authentication plugin is known as PKI-DH. That means this plugin uses public key infrastructure. There's a trusted identity certificate authority. The identity principal is the DDS domain participant. So a certificate identifies each participant, and that certificate has to be generated by the certificate authority. Authentication and key agreement is done using digital signatures and the Diffie-Hellman algorithm. So this is using commonly, common industry accepted security techniques here within the DDS model. So the second area, access control, this is done through governance and permissions. Each of these is an XML document with a schema defined by the DDS security specification. The documents must be signed by a certificate authority so that we know they're not tampered with by a potentially malicious application. The governance document is in charge of common settings for the domain, what we agree on for our security needs. The permissions document describes what each participant is allowed to do within the domain. And there'll be a separate document for each participant. And finally, the cryptographic operations. So the built-in plugin cryptographic is based on the advanced encryption standard in Galois counter mode, AES GCM, using 256-bit keys. There is a 128-bit option as well. The other option here is GMAC or GMAC. That provides message authentication without encryption. So depending on the settings you use, one of these algorithms will actually encrypt the data that goes on the network. OpenDDS 3.13 contains a beta implementation of the security specification with these three built-in plugins. These are the required ones in the specification. There are some options that are not yet implemented. That includes origin authentication, 128-bit keys in AES, the ability to relay data without being able to read it, and signing and encrypting at the full message level. Since sub-messages are signed or encrypted, we still get the desired effect on the network. And we'll see some details of this later. Let's see how this works in an actual application. So the security use case that we'll show here involves the industrial IoT, Industrial Internet of Things. In this demo application, we have a network-connected sensor measuring valve pressure. And for this application, it's just going to be a program running here on my laptop. There's also a web application that collects and displays these sensor readings. Our security needs here are to prevent imposter sensor or values from appearing in the UI, and to keep operational data confidential. So anyone looking at all the traffic on the network will not see what's happening in the system. So the demo we're going to see is built on these three software components. First, on the left, the actual device or simulator. This is built to run on embedded systems using as our demonstration platform VxWorks 7 on the BeagleBone Black, but it also runs just fine on common desktop or server systems like Windows, Linux, and Mac OS. So for simplicity of the demo today, it'll just be running here on this laptop. It's going to send data over DDS to a smart device web app, server side of the web app. This is a Node.js based server. Again, it runs on any commonly available desktop or server OS, and it uses OpenDDS's Node.js support. It communicates with the browser over RTPS and the WebSocket APIs so that we can actually see the results in the browser. So this is the demo that we'll see, and we'll do a few different demo scenarios. So step one, this is the before. No DDS security will be involved in this portion of the demo. We're going to start by launching the smart device web app that does not have a DDS security enabled. So I'm going to flip over to that and start that. Then, oh, sorry, that advanced the slide. Then we're going to start the publisher side. So this is the device simulator. This one does not use DDS security because we're still in this step one before DDS security. This is going to publish valid data. So this is our well-behaved source of data, and it's going to start publishing. Then, as we see step three here, this device is going to publish invalid data. So this stands for the malicious application on the network that's going to have us believe that something is occurring in the real world with these sensors that's not actually happening. So let's see what this looks like in the web view. What we see here is that the pressure reading is varying wildly. This number in the middle, and we see it even graphed. The graph is having a hard time with that. It's going between these real readings that are always under 100, so 70, 85, 40, whatever it is, and the imposter's readings, which are showing up at the 4,000, 7,000 range. So what we see in this demo is that this subscriber can't tell which source of data is authentic. Right? For demo purposes, we've made these invalid readings wildly out of range so we can tell. But an actual malicious application could do whatever it wants. So I'm going to stop those and we'll get set up for the next stage. Okay, step 2. We're going to start the subscriber side with DDS security. That is this application here, the subscriber secure. And then again, we'll have those 2 publishers available. They both don't have DDS securities. This is publisher insecure, 2 variants of it running simultaneously. This is now running. Let's take a look at what we see in the web view. So this is the secure side of the subscriber. You can notice the difference in the color of the title bar and the locked padlock at the top. This is somewhat uninteresting, right? Nothing's happening, and that's good. That's an important aspect of DDS security, that this data that is not secured on the network is not being seen by this subscriber. So this is a completely static snapshot here of whatever was last running in the demo, but no values are being updated. Now let's go on to step 3. In this step, we have a secured device. So this time we've gone to the embedded device and we've updated it with security enabled application. We'll see some details of how that works in a moment. It needs to be deployed with certificate, private key, and signed configuration files. So let me make sure to stop the other ones and I'll start that up. Okay, so this is the secured publisher. But for this step, what we're going to see is the insecure subscriber side. So that's starting up, and let's take a look at its UI over in the browser. Okay, so this is running, and we can even see based on that one, that data is being published, but it's not seen here. So again, this is an example where we're not receiving data from DDS, and that's exactly the outcome we desired. Because this subscriber can't authenticate with the publisher, and even if this publisher was otherwise sitting here publishing on the network, it's encrypting that data with a key that this subscriber doesn't know. So there's no way for this subscriber to get the data that's being sent. Okay, I'm gonna close those. Okay, now in step 4, we will actually employ security on both sides. So this is the secure subscriber and the secure publisher in step 4. So now, once again, we have data flowing, and we can even get the graph to update. There it is. So data is coming into this secure application, and it is the data we expect. In a moment, we'll discuss some details of what's actually happening behind the scenes in DDS to make that work. But now let's complete the picture. So the fifth and final step of the demo shows all of these components running simultaneously. I'll leave these running, the ones we had from step 4, which were the two blue ones on the bottom, the secure publisher and subscriber sides. And I'll start up the other components here, which is the invalid data in secure publisher and the subscriber side. And I'll switch back to the web view. We can even see these side by side. Now we have the system in essentially the state we want, which is on the secure side here, we have the correct readings. They always fall between 0 and 100. And once in a while, you'll see an alert pop up that's just to show what the web app can do. So it looks for values that are over 75. On the red side, the insecure application, we show that these are the invalid values that are way above 1,000. So in this demo, we've essentially separated these two parts that would normally be in the same DDS domain into the secure and insecure portions. But there's a lot of other configurations that are possible with DDS security. What has to happen in the code to enable security? Not a lot. So the way the DDS security spec works is that it adds a quality of service policy to the domain participant QoS. In the application, we need to fill in this quality of service policy with all the appropriate settings. Once that's done and the participant's created, there are no other source code changes for an application to use DDS security. Everything else is happening within the middleware. So there's a lot on here, and we'll talk about these in detail coming up. But as you can see from the names of these properties, we're configuring the DDS security authentication and access control plugins with the data that they need to do their job. Okay, so and in detail here, there were 6 different files that are being provided. And we'll talk about those as we go into the next slide. So what are these 6 files and how do they get set up? Well, the first one is the identity certificate authority. So this is a .pem file, and it's the certificate for the CA. It can be an existing CA or one created just for this application. And that would be shared, among all participants in the domain. Next is the permission CA. And this can also be the exact same as identity CA if you'd like, or it can be distinct. The reason why you might want a distinct CA is that this allows the private key to sign the XML, but not to issue new identity certificates. So that's completely a decision that's up to the application, whether those should be the same or different. The next group defines the particular participant that this application will be. So this is essentially the identity principal in the security model. This participant was issued a certificate for its identity. And in this case, it's just called test participant 01 cert.pem. This was issued by the identity CA. Then there's the private key. So because we are authorized to act as the security principal, we have the private key for this certificate. And the final 2 files are the configuration files, governance and permissions. They are XML data, but as you'll see from the names, they're actually P7S files. That's because they're not just XML documents, they're signed documents. So the permission CA needs to sign these so that they're not tampered with, and we'll see how that gets used in a second. The governance file has rules common to all participants in the domain. The permissions file is for this particular participant, and it contains within it its subject name that has to match the certificate. So graphically, we'll set up configuration in both the governance and permissions files. Then those files get signed, so they're effectively wrapped within this secure envelope. And those are given to DDS. Here we have the view of process A. So it's creating a participant, a publisher, data writer, all the normal things that happen in a DDS application. But it's also, as we saw a few slides ago, using the QoS to provide these signed documents to the OpenDDS libraries. And that's used within the DDS security implementation. Notice in this part of the diagram, we're showing the network in process B. That's important because having a signed document isn't just a local aspect of DDS security. It's also part of the security protocol. So in order for process B to trust that process A can interact with it over DDS security, it will see the configuration file, the signed permissions for process A, and can verify that signature. So this is an important part of the security model. Let's take a quick look at what's in these files. So this is not a complete governance XML, but it's a portion of the interesting part of the governance XML. It shows which domain we're configuring and has a number of domain-wide settings. In the simple case, these are just Boolean values, true or false. So the first one we're seeing here is allow unauthenticated participants. In our example, this is false, but it could be set to true, which allows some limited interoperability with non-security DDS applications. There's also settings for access control. And then one I've highlighted here with the call out is discovery protection. So DDS discovery data also goes across the network, and that can be secured as well based on these settings in the governance file. Below the general domain settings are the per topic settings, so topic access rules. Each topic rule can have an expression. Here in this simple example, it's just star, right? The wildcard for any topic. And the simple demo we just saw only has one topic, so we didn't do any other topic by topic configuration in it. These various settings will then occur at the topic level, so we can actually enable protected or secured discovery, and we can configure what kind of cryptography we want on it. And so we'll look at these metadata protection and data protection options a little bit later as we talk about the details of cryptography, but it's here in the governance file that they're set. Then we have the permissions file. So similar to the previous slide, this is not a complete permissions file example, but it does show the interesting parts of it for this demo. The permissions contain a subject name. This is part of the document because an important part of the permissions file is that it is granting permissions to a certain security principal. And the security principal is based on the identity certificate, which is the domain participant. So this subject must match the subject in the identity certificate. Or if it doesn't, this will not be treated as a secure DDS peer by anyone else on the network. Permissions have a start time and an end time, so they can't expire at a certain time. And they contain a set of allow and deny rules followed by a default. In the simple example, we have an allow rule. Default is deny. So for any action that needs to be checked against permissions, the built-in plugin will go ahead and look for a rule that allows that action to happen. In this case, let's say we're going to create a data writer, because this is happening in our device simulator application that needs to publish into DDS. This rule, assuming our domain ID matches, which it does in this case, allows publishing on any topic. So we could have written this to be specific to the topic. In this case, it's just star. So this participant can publish, create a data writer for any topic in this domain. The rules are checked in the order they occur in the file, and if no matching rule is seen for the access control check, it'll go to the default. So what actually happened when we ran that demo? Well, a number of things have to happen to get all of the security built-in plugins set up. And we'll start with authentication, because that's essentially where this process starts. As with non-security enabled DDS, when using RTPS discovery, the first message that's seen is an SPDP message, the Simple Participant Discovery Protocol. So this is a peer-to-peer discovery system that's been part of the RTPS specification since the beginning. And these two participants can discover each other because they each receive each other's message on SPDP. With DDS security, additional information is provided inside that message, which announces that this is a security-enabled participant. Let's look at participant 1. When it receives that peer discovery message, which has security information in it, it knows it can send a handshake request over to participant 2. Participant 2 can receive and process that handshake request and generate a handshake reply, which comes back to participant 1. It can receive and process that reply and send a handshake final. Now these two peers have completed their authentication process. So each pair of security-enabled participants will complete a three-way handshake, as we've seen here. What actually occurs during this handshake is a little complex, so we're not getting into all of it. But the important parts are that the certificates and permissions documents are exchanged. The digital signatures are verified, and the Diffie-Hellman key agreement algorithm runs. This DH key agreement will be important later as we see cryptography, because these two participants will need a common shared secret, and that is provided by this Diffie-Hellman key agreement. Each pair of participants that authenticate will have their own shared secret. Next, we'll look at the access control plugin. So the access control plugin is responsible for our domain-wide configuration as provided by the governance file. It checks that actions of local participants are allowed. So this sequence diagram is from the OMG DDS security specification, and it shows calls like the validate remote permissions and check remote participant. This is the third bullet over here. We're enforcing permissions of remote participants. This is the key ability of the access control plugin. Because if there was a malicious participant on the network, it could still do some actions that locally a normal DDS security application would not allow. So let's say that this potentially malicious participant is writing to a topic that it has no permissions to. What's important for access control is that on the receiver side, our participant 1, we're checking that there actually is access provided in those permissions for participant 2 to write to this topic. And we can ignore entities like readers or writers that are not authorized. And we'll take a look at the cryptography plugin as the third major portion of what's going on here. The crypto plugin is responsible for 3 different areas: generating keys, exchanging keys, and transforming data according to these various protection operations. So we use this term protected because things are configurable in DDS security. So protection could be none. So that depends on the governance file, and we saw some of those settings before. If the protection kind is none, then the crypto plugin does not have to do any encryption at this point. Maybe it's just a topic that's not going to be encrypted, or it's a level, and we'll see these different levels between payload, submessage, and message that doesn't need to be encrypted. The next protection kind is signing. So signing provides an authentication code along with the data. The data is not encrypted, but the receiver can verify that it's not been tampered with or sent by any unauthorized third party that doesn't have the appropriate key. Then we have the encrypt protection kind. Encrypt actually encrypts the data with AES GCM, and the data on the wire will not be visible to anyone looking at that. There's additionally origin authentication provided by the specification that is not implemented by OpenDDS at this point, so we won't discuss that further in this section. So looking at the diagram here, what has to happen for cryptography to work, especially in these one-to-many scenarios? So here we have a data writer. To be an efficient DDS data writer, we're still going to take advantage of multicast. So we need a way to write data samples in a multicast-friendly protocol so that data reader A and data reader B can both receive them, but they're protected, in this case, let's say encrypted, with a key that the data writer knows. Well, the DDS security system does this through key exchange. So the diagonal lines shown here are key exchange between data writer and reader B, and on this side between data writer and reader A. When these applications join the network and authenticate with each other, they have this Diffie-Hellman derived key or shared secret that we were discussing before. That is used to encrypt the channel between the data writer and data reader A that they can use for key exchange. Because the keys can't be sent in the clear on the network. That would defeat all the security work we're doing here. Instead, each pair of authenticated participants has a way to send each other encrypted messages for key exchange using their own derived keys from Diffie-Hellman. So in this example, the data writer is going to write the actual data the application cares about, in our case, those valve sensor readings. It's going to encrypt the data with its session key and send it as RTPS data through multicast or possibly through unicast, however it's configured. But the important point is that it's capable of multicast. Both A and B will receive that, and because they've both done key exchange with the data writer, they're both able to decrypt the data, but an unauthorized third party is not able to. So there are some terms on this previous slide that need a little further description, and those involve some RTPS protocol details. Because we can configure for protection at the level of the payload, the submessage, or potentially the message, let's see what those look like in RTPS. The RTPS header is followed by any number of submessages. Submessages can be generated by a data reader or a data writer, or they can be ones that are just internal to the infrastructure. And for data submessages, there's a data payload inside them. That data payload is the binary representation of the data we're sending. So for those valve readings that we saw in the demo, we have the valve reading, serial number, everything else is actually in the message encoded as binary. So notice here that there's this nested structure. A payload is inside a submessage, which is inside a message. So if our goal is just to have an encrypted DDS system, probably the most straightforward way to do that is to go ahead and enable the submessage level encryption, because the payload will be encrypted as part of the submessage. So we don't have to enable payload encryption apart from that. We could, but that effectively encrypts twice, right? It encrypts the payload, puts it in a larger submessage that has sequence numbers and other things in it, and then encrypts all of that. So what to do with these various levels is controlled by the application through the governance file. What we see on the right-hand side of the picture is what the crypto plugin is actually responsible for doing. It takes the message format that we see on the left and encodes it, transforms it into this format, where an individual submessage turns into a secure prefix, secure body, and secure postfix. And then potentially a serialized payload will turn into a crypto header, serialized payload, crypto footer. So the rest of the protocol details probably aren't as important in this presentation, but they can all be found in the OpenDDS documentation and the OMG DDS security specification. But it's important to remember this nested structure. So if we go back and look at the governance to review it, what we see here is that what the governance file calls metadata protection is the submessage level. Fortunately, it's a different term used. And then data protection is the payload level. So those different settings of none, sign, and encrypt can be applied here. And that effectively configures what the crypto plugin will do for data writers on that topic. Okay, so we've gone through and just to review these various aspects of the system that are occurring when we run that secure test: the authentication step, access control, and the actual encryption. So what comes next? Well, the beta is now released, and we expect security capabilities to mature as users get experience with it. And you can participate through either the community support model or the commercial support model. The community support model includes posting on the mailing lists, adding to the FAQ, submitting GitHub issues and pull requests. And through OCI commercial support, we offer design and architecture support, custom development in the middleware or in the applications, testing, analysis, and integration support, and training and consulting services. An example, what we're currently doing in our engineering team is we're working with the client, assessing the viability of using DDS with security in a next generation architecture for high rate data dissemination. It's starting with a baseline study to look at needed integration patterns and how good of a fit DDS is to those application needs. Also being assessed are the DDS security features and the benefits they provide, understanding DDS footprint, especially with resource-constrained environments, and the scaling and reliability of DDS in this proposed system. And we're already seeing good results from this. The various DDS quality service policies show a very good alignment to the needs of the application. The flexibility of DDS security allows much tighter security decisions to be made. And here we're talking about things like configuring different topics for not encrypting or signing only, secure discovery or not secure discovery. There's also the access control flexibility that fits with the needs of the application, and being able to use an open source DDS aligns well with distributed application development. So this is just one example of the ways we work with clients to make DDS and DDS security work for them. If there's any questions, I think you've probably submitted some to Nikki. We're probably a little bit short on time because of our network outage, but we'll see what we can do.
Yes, thank you, Adam. So we do have a couple of questions. And as a reminder to everyone, if you have questions about the material that was covered here today, please type those into the chat box and we will read them aloud and we will ask Adam to answer those. The first question we got just a few minutes ago, and that question was, when will the official release be?
Development post data, what we discussed here. So what's important to keep in mind is that OpenDDS is a completely open source product. There is no software in here that are licensed for. And that means that the product moves forward as contributions can be made. We don't have a particular roadmap for that. That happens based on OCI's contributions, certainly, but also how different users will contribute to it as well.
We got some feedback here that Adam was difficult to hear during that response, so I'm going to have him repeat that response.
Okay, well, I'm not really adding too much more than we've said in this slide. So keep in mind that OpenDDS is completely open source, including all of these security features. We are not charging license fee for any aspect of OpenDDS software whatsoever. And that means that, like any other open source project, OpenDDS's software progresses as contributions are made. And some of those contributions come from OCI, and some come from external organizations, whether they're working with us as part of commercial support, or they're just external contributors to the system.
Next question. Is there a hit on CPU resources when security digital certs are fully implemented?
So we expect there to be some overhead from this. It's not something that we have measured yet, but there would be a little bit of overhead, especially in discovery and authorization and that initial authentication step. However, once discovery and authentication are done, the overhead is expected to be pretty minimal because the well-known AES operations can work on the data and just as it flows through the system. So because we're at a beta at this point, we haven't done those scientific measurements of performance hit, but that is something we would expect to do in the future.
Okay, we have one more question here. We've got about 3 minutes left of time. And that question is, can a participant update their permissions after they match?
Right. Okay, so to take a look at that, let's look back at the permissions XML. So the way this is defined by the built-in plugins, the permissions are essentially fixed because this document has to be written and signed by the CA for the system to work. So at least with the built-in plugins, there's not a lot of dynamically changing permissions available to the system. However, we're seeing this at the scope of a domain participant. So it would be up to an application whether that would be acceptable for the application to essentially tear down one domain participant and set up another domain participant with revised permissions in it.
Thank you, Adam, and thank you everyone for joining us here today on the webinar. As a reminder, we did record today's session, so you'll receive an email with a link to the video, a link to the slide deck, which was actually already put into the chat box if you were following there, and you will also receive the video and everything else that was covered in terms of the online resources that were mentioned. And please stay up to date with all of our upcoming webinars by visiting objectcomputing.com/training. Thanks again.